You are welcome back from break. Let's continue from where we stopped. Let's consider locus 4. This is a locus of points equidistant from the intersection of two lines. And that locus is said to be a circle. Remember, two loci now are giving us circle. We have a locus that gave us circle the other time. That's the locus of points equidistant from a fixed point. It gives us circle. Also, locus of points equidistant from the intersection of two straight lines is a circle. This is the explanation. This is a straight line. Another straight line. A, O, OB. These two straight lines that intersect, their point of intersection here is the focal point in this regard, not the two intersecting lines. Remember, we have considered a locus of points which refer to the angle bisector of the two intersecting lines. But in this case, we focus on the intersection point. An intersection point is a fixed point. Do you understand? The point of intersection is the focal point here, and it is a fixed point. Now remember, in the first circle-oriented locus, we say the locus of point equidistant from a fixed point is a circle. Also, this intersection point of these two intersecting lines, their intersection is a fixed point. So the locus of point equidistant from that fixed point also will be a circle. So, example 1. The locus of a point equidistant from the intersection of lines this and this. We are given the lines in equation form. Whether you are given in equation form or just as two lines, we mean the same thing. What is important is for you to know that the point of intersection is a fixed point. Just like this point of intersection of these two lines is a fixed point. So any locus of point equidistant from this fixed point will be a circle. Do you understand? So the answer here is a circle. The locus of a point equidistant from the intersection of lines this and this is a circle. So just master it, and anytime you see it in the exam, knock it down. That is it. Let's consider locus 5, which is the locus of points which moves on one side only of a straight line, and which is said to be a semicircle. Anytime you hear that a locus of points moves on one side of a straight line, that locus is a semicircle. Let me demonstrate it here and you see. Let's say this straight line AB. The locus of point that moves only along this line will be the locus that will move like this, and end here. And it will form a semicircle. How do I prove it to you? See this question. The locus of a point P, that P will be along this arc. Along this arc. Let me use the letter used in the question originally. X, Y. Let me call my own also X, Y. And the locus of a point P, which moves on one side only. No, this side is one side only. This is another side down here. It doesn't move there. On one side only of XY. So that P could be anywhere here. It could be here, it could be here, it could be here, it could be here, it could be here. Along the arc. The description here now is that angle XPY is 90 degrees. Wherever you put P along this arc, let me put it here. And if you like, you can put it anywhere. Wherever you put it, form angle there, like this. That angle P along the line of the arc there is 90 degrees. Remember the theorem in circle geometry, which says angle in a semicircle is 90 degrees. This is an angle in a semicircle, it's 90 degrees. If you don't understand, quickly remember that this is an angle, and it's angle 180 degrees, angle on a straight line. You remember? And if you want to use the theorem, which says that angle at the center is twice the one at the circumference. This is the angle at the circumference. And angle at the center, which is 180, is twice the one at the circumference, x. Meaning that 180 equals 2x. Twice of x is this. Then divide both sides by 2. We have 180 divided by 2 equals 2x divided by 2. So this is 90 degrees equals x. So angle in a semicircle is 90 degrees. So the correct option here is a semicircle, option D. Option D is the correct answer. So anywhere you see something like that, that a point moves on one side only, it forms semicircle. Let's consider example 2 under locus 5. A particle P moves between points S and T such that angle SPT is always constant. Find the locus of P. Option A, it is a straight line. Option B, it is a quadrant of a circle with ST as diameter. Option C, it is a perpendicular bisector of ST. Option D, it is a semicircle with ST as diameter. The correct option is option D. It is a semicircle with ST as diameter. The illustration is this. Let's say this is the ST. The locus P that moves such that the angle SPT is always constant is this. It's along this, it's along the arc of semicircle, such that if you say P is here, or here, or here, or here, anywhere on the arc, the angle will be the same, constant. That's the meaning of constant. Let's try this. This is angle SPT. SPT, angle SPT. This angle is 90 degrees. This angle in a semicircle, circle geometry. If you say it is like this angle is 90 degrees. If you take another point, this angle is 90 degrees. Anywhere along the arc of the semicircle there, angle SPT will be constant. That is the same, 90 degrees everywhere there. And that is semicircle with ST as diameter. This ST is the diameter, and that is the answer. We now come to locus 6, which is the last of the loci that I'm going to expose you to. A locus of points equidistant from 2 points, A and B, is the perpendicular bisector of line AB, which divides the line AB into 2 equal halves. This is what we say. Let's say this is line AB. These are the 2 points A and B, which forms the line AB. The locus of points equidistant from points A and B is the locus, is the line that divides the line AB into two equal halves, like this. This dividing line is what we refer to as the perpendicular bisector of line AB. That line is called perpendicular bisector. It's also called locus of points equidistant from 2 points A and B. So whichever description in the exam, you must be able to get it that we are describing this line, this dividing line, which is the locus of points equidistant from A and B. That is to say, that line has equal distance from A and also from B. The distance of this line from B is the same distance from this line from A. So if this point is X, then we say AX and XB are the same in length. Let's consider example 1. The perpendicular bisector of a line XY is the locus of a point A whose distance from X is always twice its distance from Y. That's not true. Whose distance from Y is always twice its distance from X. That's not correct. C is the locus of a point which moves on the line XY. It's too open. Truly, it moves on line XY, but it's too open. It's not well described. D is the locus of a point which is equidistant from the points X and Y. That is the answer. Option D is the correct answer. You can see it in the description there. That's a locus of point equidistant from 2 points. What are the 2 points here? X and Y. So that is the answer. Let's consider example 2 under locus 6. What is the locus of points that is equidistant from points P 1,3 and Q 3,5? You can see that this question is trying you on 2 different knowledge. On coordinate geometry, you are being tested, and also on loci, you are being tested. You must be very versatile on the 2. What is the locus of points that is equidistant from point P and Q? Supposing this is P, this is Q. The locus of point that will be equidistant from the 2 points P and Q will be this perpendicular bisector. So see it on the board. Perpendicular bisector of the line PQ. And that perpendicular bisector is the locus we are talking about. But you can see that our options are not in words, but rather in a question. Meaning that we are bringing coordinate geometry into it. So how do we go about that? The coordinate of P is this. The coordinate of Q is 3, 5. So if this locus is the perpendicular bisector of the line PQ, then we need the point of this bisection, the midpoint of PQ. That is what we need here at this point. And that will be the half of addition of point x1 plus point x2. x1 plus x2, that is 4 here. 1 is the x1 here. 3 is the x2 here. Addition of them is 4. Halve it, that is 2, 3 plus 5, that's 8. Halve it, that is 4. That is, find the half of it. This is the coordinate of the midpoint. This is what we call coordinate of the midpoint, which I have taught you before now in coordinate geometry. So that is the coordinate that through which the perpendicular line here cuts the line PQ. So we now want to find the equation of that line. How? Before that, you know you are going to find perpendicular equation in this case. So let's find the gradient of the first line PQ. gradient of the line PQ, I call it M1, will be Y2, Y2 is 5, minus Y1, divided by X2, which is 3, minus X1, which is 1, and that is 2 divided by 2, answer is 1. The gradient is 1. So the gradient of the perpendicular now, which is M2, will be minus 1. If you don't know, remember that I taught you that M1, M2 equals minus 1. And if you put the M1, which is 1 here, it is 1 times M2, which is minus 1. 1 times M2, that's M2, equals minus 1. So that's the gradient of the perpendicular line. We now use it. Therefore, the equation of the perpendicular line here, the equation of this line that is perpendicular to PQ will be y minus y1, which is equal to y minus y1, which is equal to m into x minus x1. Do you understand? So, the y here minus y1. Our y1 is 4 here, because we are using the midpoint coordinate for it. That's 4 equals m. The m here is the gradient of the perpendicular, which is minus 1. Minus 1 into x minus x1. x1 is 2 here. So, we have y minus 4 equals minus x plus 2. When we use negative 1 to open that bracket, that's what we get. Now, y will be equal to minus x plus 6. You know we have positive 2 there. By the time we take the negative 4 here on this side to the other side, it becomes positive 4 as well. Positive 4 plus positive 2 gives positive 6, and that's the answer. Let's see what is the correct option there. So, option D is obviously our correct option. Option D is the correct option.